Well, good afternoon to everyone, and thank you for being here. Well, now I'm going to talk about biaxial fatigue and the tension torsion UFT. So, well, this work was performed by myself and also by PhD student Henrique Lopes, Dr. Pedro Costa from and Professor Manuel Freitas from Institute Superior Técnico University of Lisbon, and also from Professor Diogo Montalvão from the University of Bournemouth, UK. Okay, well, just the outline of my presentation. I will start with a brief motivation and the objective of this work. Then I move to the ultrasonic fatigue testing machines and compare conventional ones with the ultrasonic testing ones. And then we move to the biaxial tension torsion proposal, our proposal regarding this type of tests. And we are going to talk about the horn and specimen designs. Then I will show some results from these tests, and then I will conclude with some remarks. Okay, so this is a case study that we have studied in our lab. It's a well-known mechanical component, a crankshaft. In this case, is for 8-cylinder diesel engine with a power of 3.5 megawatts and around 600 rotations per minute, which means that in this particular case, the main efforts here are the torsion and the bending efforts. So this fed around 33,000 hours, which means a huge number of rotations. So this is the motivation for this kind of studies. And as engineers and scientists, we should be aware that the new equipments are predicted for a long life period, which means more cycles, and also the proper knowledge and damage and fracture mechanisms is of prime importance. So material fatigue design must be studied under the very high cycle fatigue regime. And also, according to that, the STN diagrams must be improved. So a better understanding and evaluation of this period of this regime is welcome. Well, this is to show the graph from our colleagues, Pedro and co-workers, that represents a kind of decay of the strength of the material along the number of cycles. So the question is if the fatigue limit exists or does not exist. Well, to answer this question, we need to test above this number of cycles. And well, just to compare the classical machines, well, if you want to achieve 10 power 9 or 10 power 10 cycles, well, we take a lot of time to do that. So costs and money and time. Well, we need another way to perform this type of test. So we are using an ultrasonic fatigue testing machine that works at 20 kilohertz. So if you don't stop the test, which is not the real cases in most cases, but if you don't stop the test, we take less than a day. Well, and if you want to achieve 10 power 10, well, it's less than 30 hours. Okay, so the global objective of our research is to characterize and to evaluate the materials, the mechanical behavior of materials in all different quadrants, and which means we are talking about different loading and stress states. In this case, during my talk, I'm going to focus on this, on tension torsion loading case. So, and we are doing this for very high cycle fatigue tests. Okay, so keep in mind the principles of the resonance and ultrasonic fatigue tests. So we are reproducing free vibration work. So we are dealing with natural frequencies. And in this case, all the set of components should be working at the resonance frequency, the fundamental frequency at 20 kilohertz. So we have here the piezoelectric actuator, then we have the booster, the horn, and at the tip, we have the specimen that you want to test, that you want to evaluate the material. Okay, so the question now is how to produce a biaxial loading in the very high cycle fatigue conditions. Because regarding this type of test, this is a Biaxial test, so this is well defined and we have an analytical solution for this and also PEM. But for a biaxial loading case, it's not so easy. So we need to design a horn and a specimen that the all of number of components should be working at 20 kilohertz. So this is our proposal. The big challenge is to have all the set working at the same resonance frequency and which means another issue is should be in a specific stress amplitude ratio at the same location. So we need to specify where do we want to reach a certain stress, and we should combine the axial one with the torsional one component at 20 kilohertz. So our proposal is that we are going to use a warns that transforms the uniaxial displacement that is received here from the piezoelectric transducer and the booster, and it goes passing through the horn to the specimen, and in this tip will create a rotation movement and the axial movement, okay? So to achieve that, well, after many attempts, we reach these particular grooves that are very dependent of the slope, the width, and the depth of each groove. So it's two sets of grooves that are going to create, let's say, these two movements, the rotation and the axial displacement. Okay, so we have performed fundamental element analysis, and we have at least finally created, proposed this specimen with 3 throats, as you can see here, and we have tested them and simulated them. So here, just for demonstration, can you click on the movie, please? Yeah. Yeah, please.
Yeah, I cannot find.
No, but
It doesn't.
oh, but before it works, okay, sorry. So, but if it works, you will see that this part here is a node. So displacement is 0, which means we are going to get here the higher stresses. And if we move to the torsional component, we have 3 throats, as I said before, and we have here also 3 nodes, okay? So 0 here, 0 rotation here, and also 0 rotation here, which means, that when we combine both, we are going to reach the first longitudinal resonance mode, the axial one, around this. So the range work of this piezo is from 19.5 to 20.5, so we are in. And for the third rotational resonance mode, we have this, achieved this 20.294 Hertz. So we can combine both, okay, and we are not able to see. We move. And well, here, just to validate what I'm saying, when we reach here the 0 displacement, the axial one, we reach here the maximum axial stress. And when we consider the rotation, so we have here the 3 nodes for each throat. So we have 3 throats, and we have the maximum stresses there. So, and as you can see, if we can combine both, we reach the maximum equivalent stress, let's say, from the axial one and from the torsional one here in the middle throat. Okay, so of course we need to validate this. These studies on FEM, and well, we have also applied some strain rosettes in order to measure the deformation, the strains in the main throat here in the middle, and at the free end base here we have measured also with the laser polytech the displacement and the rotation of the specimen in order to validate our simulations, our numerical simulation. Okay, so another question that we have set after this first part of the study was, well, if I want to consider different stress ratios, how should I proceed? How should we proceed? So, and the question and the answer is this one. So if we change the torsional component, we are going to reach different stress ratios, okay? So we move on, and we have, again, back to the simulations. So we know that this drawing allows us to reach a stress ratio at least, but now we have defined different variables, let's say here, A, B, C, and R, and we are going to combine them in order to achieve different stress ratios. Okay, so in this case, so here in this part of the slide, we can say that we manipulate A, B, C, and R, okay, in order to have different stress ratios. Okay, so we run again the finite element analysis, and well, we reach different shear axial stress ratios, and we manufacture 3 different geometries. Okay, here the material that we have considered in our study, some mechanical properties, and here the 3 different one specimens. So as you can see here, we have different lengths here, also different lengths here, and also the radius are also different. Of course, we are talking about not so big differences, but we have 3 different specimens that allow us to consider and to apply different stress ratios. Okay, so here the axial one and the shear stress component. So after that, we run the tests. This is an average for a set of specimens from each group. And we also measure the crack initiation angle at the end of the test. So as you know, when you are performing this kind of tests, so the specimen do not break, the machine stops because it loses resonance. And then we pick another machine just to fully split up the specimen. So we get this. And then after that, we have measured the crack initiation angle of each set of specimens. So in this case, if you consider here the stress ratio, as the stress ratio increases, we can also see that the crack initiation angle also increases. Okay, so it's identified here. Okay, we have also looked at the fatigue fracture surface. And if you look here for each stress ratio, you can see that the torsion component is evident, the effect of the torsion component. So it's more pronounced when the stress ratio increases, as you can see here. So the marks are more predominant in number and shape. Okay. Okay, so this is the highest stress ratio that we have considered, 1.24. And as you can see here, the staircase fractal shape is most prominent and evident. So this is linked to the higher shear component that was applied in these tests. Okay, so this is the final remarks. So we have produced Biaxial specimens that allow us to, with 3 rods that allow us to perform Biaxial loading tests in very high cycle fatigue. Well, we can imagine a way to produce tests in different stress ratios. And in this case, due to the shear component, well, all the crack origin were in the surface. And well, also the higher stress ratio is linked to the higher crack initiation angles and more prominent torsion fatigue marks. Okay, thanks a lot for your kind attention.